Yeah, hello everybody. It is a pleasure to have the chance to present Professor Nataraj. I have known Nataraj for a long time now. Currently, he is the Moritz Chair Professor in Engineered Systems, and he is the founding director of the Center for Analytics and Dynamics Systems at Villanova University. Today, Nataraj is going to talk about. Actually, the talk is a question: can nonlinear dynamics improve medical diagnostics? So I will not get any of his time and let him start this interesting, I guess, talk.
Thank you very much, Sotirios. Our friendship goes back to, I think, 1986 or something.
87. I don't want to say it, but it's
It's a little
87.
scary. Yes. So let me share my screen. Thank you, Walter, for this opportunity. Let me make sure I can share it. Can everybody see my screen? Sotirios, can you see my screen?
Yes, I can. Yes.
Okay. Okay. I just want to be sure. Not able to see. Okay. There you go. Okay. Good morning, good afternoon, good evening, everybody. So it's a pleasure to be here at this conference, this exciting conference, and to talk about something that has occupied a significant part of my research over the last 15 years. I would say maybe more like 10 years. And I pose it as a question, and you will see why, because I think I have more questions than answers. So this is the rough outline of the talk. I'll go over roughly why we want to do this. How do we normally do biomedical diagnostics, and where is the field moving? And I would like to make a case, as lawyers do, for nonlinear dynamics and how it might help. And I want to pick an example that we did recently. We're working on a paper right now for nonlinear dynamics. So in that context, we worked on a problem that I want to highlight. It's called on cardiac diagnostics. And if there is time, I will. We have done maybe 5 or 6 different problems. So I would like to give a very high-level overview of that, and I'll conclude. And hopefully, we'll have enough time for questions and discussion. So we all, presumably everybody in the audience here knows what mathematical modeling is all about, especially because we typically apply to engineering systems or physical systems. And the typical objectives of mathematical modeling are you want to uncover the underlying mechanisms and gain insight to what's going on. Or sometimes, as has often happen in physics, you observe something, and you want some model to be able to explain it, some way to explain it, so you come up with a model. And often you come up with new hypotheses that you can empirically validate, and modeling is a source of that. You also sometimes want to validate your assumptions, examine differing hypotheses, and sort of, heading towards this in any complex engineering systems now is developing a platform for a computer-based experimentation, because experimentation is expensive, and it's much better if you have a high fidelity model that you can experiment. So that's I'll call it in silico, because when we talk about biomedical, it's a good word to use. In particular, in terms of mathematical modeling, nonlinear dynamics, of course, provides accuracy, but much more important, it explains unique phenomena that we observe that cannot even be qualitatively explained by linearized models, as we know. And it can lead to more efficient and safer design if we know how to do it, and of course, insight, right? So this, this is kind of a well-known motivation for developing mathematical modeling, and arguably, we've been doing this for about 400 years since Isaac, I should actually say Galileo, and then Isaac Newton, and so on. So in the biomedical world, the physics-based modeling is not as widely used. And I don't mean things like biomechanics. I'm talking about, things like the medical world, I should say, right? Where doctors, for example. Why? Well, there are many reasons, right? One reason is that the human body is really the most complex dynamic system that we know. I just started to read a book by a physicist, where he says that the number of atoms in the human body is 10 power 28, and that's a million times the number of stars that we estimate to be in the universe. We have that many atoms in our own body, right? So it's daunting, it's very complex, it's so complex, can we even start, right? That's the sort of the issue here. There are multiple spatial scales, as we know, from cells to tissues to organs and systems, also multiple time scales, microseconds to years. And there is almost every system in the body has a nonlinear and adaptive, short-term adaptive and long-term adaptive feedback control. And we have huge gaps in understanding. We still don't know how certain things happen. As for example, during the COVID, we understood that the immune system itself, is something we don't really quite know. And diagnostics is really the opposite of normally what we call analysis, right? So given a situation, we want to construct a model. So it's an inverse problem. So inverse problems are obviously more difficult. And in the biomedical world, it's even more difficult. Okay, so given that, it's difficult, and that's why it's not taken on. All right, so now let's think, pull back a little bit and look at how medical diagnostics is done today, right? And I will call the way the doctors do it, I'll call it expert knowledge. So when I say the typical process of expert knowledge is where they collect data, and the data is often heterogeneous. For example, you may collect blood pressure data, which is maybe just 2 points, high point and a low point, systolic and diastolic. You may get an electrocardiogram, which is more like a graph, a physical examination, which is very qualitative. You may get a blood test that is episodic, that just gives you some numbers. So it's very heterogeneous. It's also unbalanced in the sense that if you collect data from 1,000 people, maybe 2 of them have a disease and 998 don't have it. And that presents problems for example, for the doctor, because they're more likely to miss a bad diagnosis. And what do they do? They take the data, compare with past knowledge, and essentially do a pattern matching. And this can be their own knowledge. It can be the professional body's knowledge, which is encoded in the guidelines from a medical organization, for example. And as we know, these things evolve all of the time, and hopefully they try to get it right. But primarily, it's a pattern matching problem at a very superficial level, and often misses the mark. And of course, you treat and monitor and you revise if wrong. This is how the doctors do it. So the statistics are pretty horrendous. In fact, it's very difficult to get accurate data, but the accuracy for some diseases is as low as 10%, maybe even 0%. And some, it's more like 90%, but on the average is somewhere in the range of 25 to 30%. Okay, and this is based on fairly detailed analysis by the Institute of Medicine. And the diagnostic errors are very expensive. They cost something like $50 billion in the US, for example, every year. They kill a lot of people. They're very expensive. They're, of course, they're also resulting in deaths. They lead to disease. You know what happens with wrong diagnosis. Okay. So where does it go wrong? Like we said already, the body is too complex. And then if you think about the body as a dynamic system or a system of systems, basically what they're observing is some state variables, very few. And very often they're just looking at instant time shots of these state variables, right? So if you think about a complex dynamic system, if I did that to an aircraft, with a very superficial examination of just a few state variables, I would also go wrong. I would not be able to fly the plane, right? So that's the problem we have. The system interactions are not understood. There's a large amount of parametric and model uncertainty. Every individual is different from any other. It's very difficult to have 2 people behave exactly the same way. And the data that we have collected over the last, I don't know, maybe 200 years to do this is not sufficient to build a robust empirical model. And of course, we all know that nonlinear effects phenomena are not intuitive. So you don't expect a doctor to suddenly expect a jump phenomenon, in what he's observing, right? It's just not intuitive. And the other problem is that they kind of looking at this without any mathematical processing. And we know that, for example, I work in vibration. If I just looked at some signal, I may not be able to see what's going on. But if I just do a simple thing like a Fourier spectrum analysis, I can immediately jumps out at me what's going on, right? So without any mathematical processing, which they're not doing, even the data that they're getting is not very useful. So the use of AI and machine learning. I'll use AI and machine learning interchangeably. Some people may object to that, but let's say it's in this context, it's okay. They're kind of approximately the same. So what does AI do? Well, it learns from data, right? And now, of course, we are in big data. Everybody's collecting data. I work with hospitals a lot, and the data, they're awash in gigabytes of terabytes of data. Okay, so we say, oh, we have a lot of data, so we can build it. So there is this hype about AI right now. Everybody thinks they can solve every problem in the world with AI, right? And there are a lot of problems with that. So obviously, there are some advantages. It can replace inexpert doctors and so on. What are the limitations? It cannot be generalized. It lacks insight. It's really a shot in the dark. Okay, it's it's really a pattern recognition problem, but done at a more sophisticated level. It is a strong function of who develops the algorithm, what you put into it, and this has become apparent recently when they've been using AI for lots of problems. Okay, it's very biased. For example, it's not parameterizable. If a person puts on 5 pounds of weight and you develop an algorithm, now that algorithm has to relearn something because not valid anymore. Unlike what we do, we just change the weight in our model and now we get new results, right? And of course, it cannot be interpreted, which makes it very difficult for a doctor to use it. So the typical AI process, just to give you an idea, is the following, right? You take the data, you have to pre-process a lot. Medical data, you have to pre-process a lot because there is missing data. There's a lot of confusing variables that interfere, for example. And typically you abstract what are called features. Features are aspects of a signal. So to give you a very simple example, if I have a complicated signal that's, let's say, a blood pressure signal, I may just take 1 point from it, like the maximum value and the systolic pressure, and that's a feature, right? So you don't take the raw data, you take some aspect of it, and then typically you separate it out and you basically run through an algorithm that computes the coefficients or so-called weights in a process called training, and then you can do a lot more sophisticated things with this, and eventually out of that comes out what's called a classifier or a neural network or a support vector machine, whatever. There are many variations on this, and then you test it with data that you've not seen before, and you hopefully that's good enough that you can make the decision with that. Okay, so let me make an argument for nonlinear dynamics. So if AI is working so well, the problem is AI doesn't work very well, and at best it's reached about 25 to 30% right now for a lot of diagnostic problems, and we've done a lot of that in a lot of our projects. So and I'm just quoting some of the people here, and this really I thought these are the best that I could find, which are very insightful. Basically, the idea is that the normal physiology is governed by nonlinear dynamics. It's apparent now. It's not linear dynamics. Everything is nonlinear. This is normal. And in fact, sometimes the pathological condition, sometimes it actually becomes closer to linear, as in epilepsy, for example. There is Bruce West, who actually says the variability is more indicative of health than the average. So we should not be looking at average, but the entire medical field tries to meet the average when the variability is indicative of a healthy individual, which is very interesting when you think about it philosophically. And I think some of the points already made here. Okay, and then there is some thought that multifractal cascades is how you want to be operating on, and homeostasis, which is kind of maintaining a certain constant condition, is probably not normal for a human being. Okay, so again, we can go deeper and deeper, but let me get to an example quickly. So our thought is, nonlinear dynamics is certainly limited, or any kind of modeling is really limited because we don't know so many things about it. AI is really limiting because it's very short in the dark. So can we inject some of nonlinear dynamics to reduce uncertainty, to improve parameterization, with artificial intelligence or machine learning to make this better? Okay, so what I'm going to show you is a sort of an example of how we could do this and how it gave us reasonably good results. Potential, of course, is that you could build an individualized in silico model. So looking out, I don't know, 50 years from now, I could walk into a doctor's office where they would have a model for me, along with every kind of analysis from analytical to numerical that can predict how I'm going to behave, and it keeps updating it as a with sensors, right? That would be pretty awesome, and probably we may get there. Okay, So my point is that we can combine it. So let's look at a sample problem. So this is a very simple, sketch of a cardiac defect, and a cardiac defect is abbreviated, of course, like all medicine. They have long abbreviations. It's called CLBBB, and that is complete left bundle branch block. So basically, what happens is, as you might already know, the heart is triggered by electrical impulses coming from the brain and several neural node centers in the heart and several places, and that triggers the heart's different chambers to contract and expand at a certain time, which is carefully pre-programmed and then adapted as the body's needs change. Okay, so what happens here is that you can see kind of a branching here, the blue branch below the his bundle, that often leads to a blockage either on the left side or the right side. And this is a very common defect, and a lot of people really have this, and many people are not even aware of it, right? And potentially, of course, it's lethal, and you can die. But many times, nothing happens to you. Okay, and this is the doctors look for. Of course, as you can imagine, if it's like a motor. If you think of it as a motor, an actuator, if the electrical voltage is interrupted, the operation of the motor is interrupted, right? So that's kind of basically what happens to the heart. Okay, now the way we monitor the heart's electrical impulses, usually using an electrocardiogram or an ECG, and typically the doctors kind of identify these peaks as PQ, RS, and T, and all of these numbers where they appear and what the magnitudes are, what the shape is, and all these things are indicative for to diagnose a particular disease. Okay, and they use this, and there's very heuristic. They've just developed it over the years, and they get very good at it, in doing this. But so what we did was we said, is there a mathematical model for this? Well, first, you need data, because you can do anything with the mathematical models, but the data is what really tells you, how good something is, right? So, and Physionet is a database up at MIT with actually a collaborator and colleague of mine, Dr. Roger Mark. He runs this. It's been run for 20 years, and it's an excellent data set with high frequency kind of data that we look for. And it's got about 20,000, almost 22,000 ECGs of 22,000 patients, with about 10 seconds length, 500 hertz sampling, and they have healthy and the two blocks I talk about, the left and the right blocks, as well as some other defects. Okay, so that's the data, right? And then we look to see if there is a mathematical model that would generate the ECG signal. It turns out that there was a model developed by McSharry and colleagues in 2003, which is really very cool. It's very nice. And basically what it is the limit cycle in the XY plane. And then in the Z-axis, you get this, projection that gives you this variation from peak to peak, right? So the ECG goes on, and there are variations as this goes. So that variability is indicative of a lot of things, and that can be tuned using these parameters as primarily the form of Z. And it also includes, for example, the respiratory frequency, which normally is taken out of the EKG, because that's another external, additional, just an non-autonomous term. Okay, just an external frequency. Okay, so this is a nonlinear set of equations that you would tweak the parameters. There are a lot of parameters, that's something like 15 or 16 parameters that you need to tweak to do this. Okay, so what we did was we looked at this data, and we actually developed, fairly well good parametric fits. And using the real, so this is one example of the data versus the model, and you can see it's a very good, and this is a sick individual, and it's a very good fit. Okay, it's it's missing a few things, but it's considering it's just taken off the hospital bed. This is a very good. So this model is quite good. Okay, and then we looked at all of these data to see, and then what we did was we kind of did this, took this data, fit this to the model, right? And then because there are so many parameters, we kind of kept most of the parameters constant, and we just looked at two parameters that we thought were significant. And this is, took quite a bit of time to kind of zoom down on this. So you find that all the red here is the ones with the left bundle block, and the black has no defects, right? So you can see there is in this parameter space, there is some separation between them. Not perfect, but there's some separation between them. Okay, so just to show you that you can do this with the data. Okay, so all right, so then how do you diagnose this? Okay, well, if the first thought comes to you is, okay, let's look at, for example, you can go back to this data, you can look at all these points and say, is the frequency changing? Is there a, for example, a subharmonic bifurcation, for example, or something that occurs, right? um, or maybe like a half bifurcation or something like that, but there isn't any that we can identify, that we can prove from analysis. In fact, the frequency content doesn't seem to change across this large spectrum of patients, normal versus defective. So really difficult to kind of predict from the frequency. The amplitude changes, but it's not consistent. Okay, so uh, so for example, we did look at one example or a couple of examples where you can see that there is a big difference between the S wave and the T wave, which is kind of what you're seeing in a phase plane plot here of Z versus D dot. Remember, I talked about PQRST. So if you kind of look at the difference between the S and the T wave, that difference is encapsulated in this phase plot, and that kind of shows that if you have a block, it shows up as distinctly different from the one it doesn't have a block. Okay. However, if you look at a histogram of the normal, which is on the left-hand side, and a defective on the right-hand side, you don't see that much of a difference. This is a histogram of all the patients, 22,000 patients, and you don't see that much of a difference. So you cannot just use the amplitude to tell you what's going on, right? So, the information is hidden further in it. So let me just run through this quickly, because this is not, I'm running out of time. So, we all know about phase space, right? So we've evolved a method, and you can look at the accompanying paper that will come out for some details. But we evolved a method by which you can kind of look at the phase plane and define sort of the density of the state space using a kernel, and use the features of that density function that you see on the bottom here. The top is actual phase plane, to effectively characterize the nonlinear response of the system. Okay, so we've used it for other systems, and we said, why don't we use this for this problem? And here is the sort of the flow chart of how we did this. We are comparing two different things here. The left side is where you were using this nonlinear dynamic feature that's coming from the model, that we are now extracting features out of that. There's a lot of processing going on here, mathematical processing. But then we're feeding this into a neural network. So the left bottom that you see is the neural network. So it's a combination of the neural network and the nonlinear model. And the right branch is completely neural network of a kind called a deep neural network. And we're using what's called a stacked autoencoder, which is now considered to be the best algorithm AI can offer for medical diagnostics, for cardiac diagnostics. Okay, so we're comparing with our method with the best that AI can offer. And so, and again, I'll skip this because this is, except for the very last point. So there are many metrics on how you determine this, and the main thing is sensitivity and specificity. Sensitivity is a measure of how good a test is, whether it tells you the patient really has a condition or not. A specificity, how well it rules out a diagnosis if a patient does not have the indicators. Okay, so if you look at this is sort of the example results. If you just look at the red, it compares the method where we integrated some information from nonlinear dynamics into the machine learning, and compares it with the deep learning, which is considered to be the best approach available. You can see that there, accuracy wise also it's 97 to 90, precision specificity is 97 to 93, but look at the sensitivity, which means it's only 47%, which means a lot of the times it's telling you that you have this problem when you don't. Okay, which is the doctors hate to do, right? So we suddenly, with fairly simple work, we've shown that when you integrate nonlinear dynamics into an artificial intelligence algorithm, it consistently outperforms deep learning. And this is across large numbers of patients, and there's a lot more to it than what I'm showing here. We've done a lot of problems. I'll just mention maybe the one in the middle, the CPR. It turns out the CPR is only 15% effective in terms of survival. And CPR is a the cardiopulmonary resuscitation is a very uh, 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 it's a very nonlinear process, and we've begun to model it, the nonlinearity, and integrate this in the administration of CPR, trying to see if we can improve the CPR process to improve survival. So that's talk for another day. So let me just finish saying medical diagnosis is extremely difficult. Current methods are not very effective. Nonlinear dynamics can help, but the road is long. There is a lot more that has to be done. And we think it helps because nonlinear dynamics helps you with the parameterization, improves generalizability. That means it applies in situations where you've not seen it before. Introduces a structure to the model, which is very unstructured in a sense with a neural network. It potentially helps with prognostics. That is, can we predict how the disease gets worse or better? It of course needs collaborative work. You have to work with doctors. They have to tell you what's important or not. Very challenging, but it's very rewarding. Of course, high social and economic impact. I would like to acknowledge grants from NIH over the last 50, maybe 12 years. We've been working on several different grants. Of course, my students and postdocs were not listed on the paper here. These are the additional students and postdocs who had some inputs over the years. Collaborators were all doctors at Children's Hospital of Philadelphia and other places. Thanks to Walter for Nodycon. This is an exciting conference, and for the invitation to speak. Thanks to you all for listening. And finally, I just want to say, my students do everything. I just talk. So thank you very much, and I hope I left some time for questions.
Thank you, Nataraj. Very interesting talk. It is really amazing. Over the last years, nonlinear dynamics have found a lot of applications in very diverse fields. This is very, very encouraging, especially for the young people. So thank you for the interesting talk, and I open the floor for discussion. Are there any questions, any comments from the audience?
Can I show the model?
Can I also ask, Sinat, if you can comment more about the results you showed where you were incorporating the nonlinear dynamics into your results for the sensitivity? Can you comment more about how this was actually done? And this is also another question. Yeah, the model. I think it's the same question. Thank you.
So this is sort of the way we do this, right? So there is a lot of detail. I apologize that I cannot get into the detail in this talk. But basically, we are. I'm not sure I understand your question, Walter. So if you're asking about sensitivity, perhaps, or so sensitivity, which is like 48%, right? If I go back a little bit, is um, true positive or true positive plus over true positive and the false negatives. So if sensitivity is low, it's giving us a lot of false positives. So it's kind of telling you that you have something, right, when you don't. And that's because the way I think the neural network works, actually it's difficult to know why it's giving us the wrong result. So I can't even tell you. But the way it works is there's a lot of tweaking that has to be done. So I should caution you with that, right? So is it possible to get the sensitivity higher with deep learning? Perhaps, but typically when you do that, your specificity drops. So very often in neural network, it's a trade-off about sensitivity versus specificity. Okay, and we played with it until we got it as good as we could. I don't know if I answered that question, but that's kind of.
Yeah, it was more about how a fully data-driven approach, can be poor in sensitivity with respect to the other approach where you're incorporating nonlinear dynamics. But I see also other questions.
Okay, sorry. I'll answer it later for you. Let me look at the chat.
Yeah, there are two questions there, please.
Sure. So maybe this model. This is the ODE model, I think. I think Harry was asking that.
Yeah, I was wondering about the nonlinearity here. Isn't it the case that so it's I mean the first term seems to be an explicit function of time. Is that not
Yeah,
the case?
x and y just results in a periodic orbit in the xy plane, right?
Right, which is given. I mean, it's effectively cosine t, sine t, or cosine omega t, sine omega t with some amplitude. So does that mean that the first term on the right-hand side of the z equation is just an explicit function of time?
You have alpha. That should have been alpha. This should have been, I think, a. So it's 1 minus square root of x squared plus y squared. So that's how it gets coupled. And the only explicit function of time is in z naught of t. And that is just giving us the respiratory input. So it imposes another additional frequency on the signal that we actually dropped because almost all the ECG data you see in the hospital, they filter out the respiratory frequency. So, there's a standard filter, just a low frequency filter. They take it out. It's about 10 breaths a minute or something like that. And then, so we did the same thing. We just took it out. So there is no other explicit function of time in there. It's all embedded. The nonlinearity is embedded in all of those what look like parameters in terms of x and y. Hope that explains.
Nataraj, there are two questions in the questions and answers. Can you read them, or do you want me to read them for you? Can you see the questions in the Q&A?
Yeah, I'm looking at it. One was to show the model.
That's Q&A. Maybe you can read.
Oh, Q&A. I'm sorry. No, can you read it? I don't see it anywhere.
Yeah, there is one comment by Professor Americo Cunho.
Oh, yeah.
Could you comment about interpretability in AI tools? How novel paradigms, which include physical knowledge in ML, can help in this sense?
Yeah, excellent point. So, so we've been doing some medical diagnostics for doctors, and often the question that always comes up is, well, like, why? And with this AI algorithms, they're very opaque, and you don't even know if it's repeatable, right? This is another problem. So if the doctor says, okay, I'll do this for this patient, now what happens to another patient? Can you tell me that it's going to be as valid? You really don't know. Given the variability, you really don't know. And this is the current situation, right? Now, so there is less confidence in the medical community to adapt something like that. And what we can do with the nonlinear dynamic model, or dynamic models, like we did with physics-based systems, is we can say, well, we have a mathematical model that's parameterizable. We can kind of predict what happens, and we can validate this with the data. So it gives us there's an underlying structure to it, and therefore we have some more confidence in this. It will probably still be opaque to the doctors, because if they don't have a background in this and you tell them, there's going to be this subharmonic resonance, that may not mean much to them. So I don't know if the interpretability will help that much. Okay, I joke with doctors that they should all have a basic engineering degree, because medicine is more about engineering today than in medicine, But one point I wanted to talk about this interpretability also. If you think back to the physics-based engineering we've practiced for maybe 300, 400 years, the physical world must have seemed very strange 300 years ago. And then when we started developing physics, now we take things for granted. We take things for, we understand what transition to turbulence is. But if somebody, before Navier-Stokes equation, if you looked at the flow, could you identify what that means, or understand the circumstances under which you would get turbulent flow versus laminar flow? You couldn't, right? So the to me, the physiological responses look puzzling, because we haven't spent enough time and effort and intelligence of the considerable intelligence that exists on this. Yeah, what?
Thank you, Nataraj.